Hello guys, today we'll be looking at what we call connected rates of change. Now this is a very practical and applicable topic in real life. Let us look at a typical example. Let us say you have an area where crime is increasing. As the rate of crime increases over a period of time, you might find out that the persons in the community might be moving out. So as the crime rate increases, the population size might decrease. Alright? Crime also has an impact on economy, and over a period of time, we see that impact manifesting. So the greater the crime rate, you might see a decline in economic growth over a period of time. So that is what we mean by connected rate of change. One variable having an impact on the next variable. Now on the screen I have a cube. All right, and let us say that we apply some heat to this cube while keeping the dimensions the same. Now a cube only has one dimension, that is length. All the sides are equal. So we know that we can actually determine several things about a cube. We can determine what the volume is. We can actually determine what the total surface area is. So let me start with the volume. We know that the volume of a cube, V, is equal to L cube. All right. Now let us say that when we apply heat to this cube, it might expand, which means that the length might increase. And of course, this length is going to increase over a period of time. So we can actually talk about the change in length with respect to time. And that is going to be dl over dt. However, we know that there's a connection between the volume and the length. All right. That connection here, see, notice that we have V equal L cube. So we can talk about that connection, which would be dV over dl. But if the length of the cube increases over a period of time, so will the volume of a cube. So now we're going to be talking about dV over dt. So there must be a way to connect all of these rate of change or all these changes with respect to the cube. Now let us see what happens. So what if I want, ultimately, once the length of the cube change, is going to affect the volume of the cube. And that volume is also going to change over a period of time. The connection we have is between the volume and the length of the cube. So we're going to end up with dV over dl. Now, can we actually connect all these three variables? Let's see. So ultimately, the volume of the cube will change, dV over dt. Now, what if we consider dV over dl? How can we break this down so we actually get dV over dt? Notice the answer is here because we are saying that the length of the cube is going to change over a period of time. So if I were to multiply this by dl over dt, what will happen? Notice we have the dl here and we have dl there. So when we break this down, we're going to end up with dv over dt. So ultimately, we can actually say that the rate of change of volume with respect to time, or the change in volume with respect to time, is equal to dv over dl times dl over dt. Now, if the volume of a cube expands, so will the total surface area. Alright, the area of all the faces will also increase. Now, a cube has 6 faces, and all of them are squares. So we can talk about the total surface area, which is going to be 6 faces. The area of a square face is going to be L squared. So we have 6L squared. Alright. Now, of course, that change in the dimension, which is the length, will also impact the change in the area. So we can talk about the change in area over a period of time. So if the area is changing with respect to time, that will be dA over dt. Good. The connection we have here is between the area and the length. So now we're going to have also talk about dA over dl. Now, because the length itself will be increasing over a period of time, which impacts the area increase, we know we have dl over dt. So can we connect all three of this? Indeed, we can say that the rate of change of area, or the change in area with respect to time, is going to be equal to dA over dl times dl over dt. And that is what will happen. So we can look at the rate of change of the area, we can look at the rate of change of the volume, whichever one comes in the question. You just have to learn to make that connection between them. Here's an example of a typical question that you could be asked. The radius of a circle increases at a rate of 5 centimeters per second. Find the rate of increase of the area when the radius is 4 centimeters. Now let us start out with something that we know. We know that the area of a circle is equal to pi r square. So there's a direct connection between the area and the radius. So if I increase the radius, then ultimately the area would be increased. Alright, but what am I really interested in? I'm interested in the rate of increase of the area, which is dA over dt. So I'm going to be using my connection here, which is the connection between the area and the radius, which will really give me dA over dr. Good? Now, of course, when I increase the radius with respect to time, the area also increases. So I'm going to multiply this by dr over dt. And notice if we were to try to eliminate this thing, the dr would cancel the dr. So we have dA over dt. Alright, let us find the rate of change of area with respect to the radius. So we have area equal to pi r square. So we can say that dA over dr is equal to, we carry the 2 to the front, so I'm going to have 2 pi r. Now, at this instant, we are told that the radius is 4 centimeters. So I can actually say dA over dr is equal to 2 pi times 4, which is going to give me 8 pi. Good. So this is a change in the area with respect to the radius. Now, let us go back and put everything inside of the equation that we have here. So we're going to have dA over dt equal, and let's go back up here, equal dA over dr, which we found to be 8 pi. So this is 8 pi multiply by the rate of increase of the area, which is dr dt. And in the question, we were told that the rate of increase is 5 centimeters per second. So if it was decreasing, it would have been a -5. Good. The radius is increasing at a rate of 5 centimeters per second. So what it means is that I'm going to be multiplying my 8 pi by 5. Now this is going to break down and give me 40 pi. Bear in mind the units that we have here. We have area with respect to time. The area is going to be in centimeters square. So I'm going to have 40 centimeters squared per second. All right, that is one way of writing it. Or I could say 40 centimeters square second to the minus 1. Also means 40 centimeters square per second, whichever one you use. This is example 2. A spherical ball is melting uniformly at a constant rate of 2 pi centimeter cubes per second. And this should be at what rate is the radius decreasing when the radius is 3 centimeters? Let us talk about some key things in this question. It is melting, which means that it's getting smaller. It is uniform, so it's still maintaining its spherical shape. But because the thing is decreasing, we're going to have a negative involved here. But let us talk about what we know first. The volume, because notice we're not talking about area in this case, we're talking about volume. The volume of a sphere is equal to 4 over 3 pi r cubed. Good. But what we're interested in is the rate of decrease of the radius. But we can still start by establishing our formula. We know that dV over dt, which is the rate of change of volume, would be equal to the connection we have here, which is volume and radius. So it's dV over dr times dr over dt. So at the end, we're going to have to transpose this thing for dr over dt. What we have in the question is the rate of decrease of the volume, which of course that is -2 pi. So we know that. We know that dV over dt is equal to -2 pi. So we could probably even go ahead and write that there. So that's -2 pi here. What about dV over dr? So we have the volume, which is 4 over 3 pi r cubed. So dV over dr, we carry that 3 to the front, so we're going to have 4 pi r square. And notice that this formula is actually the total surface area of a sphere. Good, that is critical. So it says when the radius is 3, all right, so it means that dV over dr is going to be equal to 4 pi times 3 square, all right, which is going to give me 9 times 4, so that's 36 pi. So let us go back down here now and put everything together. So we have dV over dr, which is 36 pi times dr over dt, which is what we want. So all we have to do with this is simply transpose the equation. So we could actually divide both sides by 36 pi. So when I break this down now, I'm gonna have dr over dt, that's negative 2 pi over 36 pi, that is going to give me negative 1 over 8. All right, and the unit here is centimeter, so this is centimeter per second. So the radius is decreasing at our, well, the radius is decreasing at negative 1/8 centimeter per second at a rate of negative 1/8 centimeter per second. Now note, because I said it's decreasing, I don't have to mention the negative, because once I say decrease, that automatically tells me that the thing is going to get smaller. So that means it's negative. So I can say it's decreasing at a rate of 1/8 centimeter per second.